So here I have the first 5 of these expanded. And to expand it, you multiply, well, say we get to the second one, a plus b times a plus b. Then we can take the answer to that and multiply by a plus b to get the next one. The answer to that and multiply by a plus b to get the next one. So if you're doing a plus b to the power of 5, you could take the answer to a plus b to the power of 4 and multiply by a plus b. But if the question was just to expand a plus b to the power of 5, you have to do all of that other work first and then multiply by a plus b, which is like a lot of work, right? But there is a shortcut here. It has to do with this, which says in the expansion of x plus y to the power of n, written in descending powers of x, the general term is t k plus 1 equals n choose k, x to the n minus k, y to the power of k. That's the binomial theorem, and it's on your formula sheet. I'm not actually going to use it for this, but we're going to use that later today. But what I want to do before we get into looking at a formula is just what patterns do you see here? So if we first look at the coefficients of the terms, what do you notice about the coefficients? Anything? If I write out just the coefficients, the first one is 1, the next one has a 1 and a 1, and then a 1, a 2 and a 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. What's that? Pascal's triangle. So if we're going to do a plus b to the power of 5, and I don't want to actually do all the algebra, what are the coefficients of the terms in a plus b to the power of 5 going to be? 1, 5, 10, 10, 5, and 1, right? I'm going to get rid of the 1 because I'm just not going to have a coefficient, but it's going to be 1. Now look at the pattern of what's happening to the a's and b's. In all of these, the first term is just a to the power of n, whatever that exponent was. So what's the first term going to be in a plus b to the power of 5?
A to the power of 5.
A to the power of 5. And the second term, what happens to the a exponent as you go to the next term?
A goes down, B goes up.
A goes down, B goes up. So this is going to have a 5a to the power of 4. This is going to have an a to the power of 3, a to the power of 2, a to the power of 1, and then no a in the last term. And with the b's, the exponent is increasing. So we start with b to the power of 0. There's no b in the first term. The next one's going to have a b, and then a b squared, b cubed, b to the power of 4, and b to the power of 5 for the last one. Here I have characteristics of binomial expansions. The exponents of each term in the expansion have a sum of n. That's one. So actually, if you look, the exponents always add up to 5 in this one, a to the power of 5, and then you have 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5. They always add up to whatever power you're expanding it to. As the series progresses, the exponent of the first variable increases by 1, and the exponent of the second variable decreases by 1. That's what we did here. This is what Alex said. So A went 5, 4, 3, 2, 1, 0, and B went 0, 1, 2, 3, 4, 5. The number of terms in the expansion is n plus 1. N is that exponent, right? A plus b to the power of 5. So if it's to the power of 5 and you expand it, you're going to have 6 terms. If it's to the power of 6 and you expand it, you're going to have 7 terms. It's always one more term than what the exponent is. And the coefficients can be found from Pascal's triangle. Now I want to look at how would I expand x plus 2 to the power of 6. So I don't want to do x plus 2 times x plus 2, and then multiply that by x plus 2, and then multiply that answer by x plus 2, and then multiply that answer by x plus 2. And I think that was 6x plus 2's, but I don't want to do all that. I just want to use this pattern. So step 1 here, it says determine the number of terms. How many terms will there be in this expansion? 7, because it's one more than the exponent. So I'm actually going to do what it says is step 3 first. Using Pascal's triangular combinations, determine the coefficients. So I need the row of Pascal's triangle that has 7 numbers in it. Which I do have little Pascal's triangle down here, but 1, 2, 3, 4, 5, 6. That only has 6. So I need the next row, which will be 1, 6, 20. Oh, sorry, I missed one. 15, 20, 15, 6, and 1. That's 7 terms. So those are the coefficients. Then, let's see what step 2 said. It's kind of small, and oh, there we go. Write the first variable in each term with descending exponents, and write the second variable in each term with ascending exponents. So I'm going to take, in the first term, x to the power of 6, start with the highest power. And then in the next one, I'm going to have an x to the power of 5, x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1, and then no x in the last term. And then I'm going to take the 2. The first term is has 2 to the power of 0, which we don't even need to write it because that's just 1. And then 2 to the power of 1, 2 to the power of 1, and then 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and the last term, 2 to the power of 6. Then I just need to simplify that once I have all that filled in. The other ones we didn't have to simplify because it was just a variable plus a variable. But here there's some simplifying to do. The first term is just x to the power of 6, so I'll just get that 1 out of there. We don't usually write a 1 as a coefficient, so we'll make that x to the power of 6. Plus the second one, it's 6x to the power of 5 times 2 to the power of 1. So it's actually 6 times 2. The coefficient becomes 12. So it's 12x to the power of 5. So all I'm doing here is just simplifying the numbers. The next term has a 15 and a 2 to the power of 2. So 15 times 4. So 60. X to the power of 4. What's the next one going to be? 20 times 2 to the power of 3. So that's 160. Is that right? Then 15 times 2 to the power of 4, 240, x squared plus 6 times 2 to the power of 5, which is 192, just x, and then plus 2 to the power of 6, which is 64. Didn't quite all fit on one line.